ভিডিও গেছে? আমার ভিডিও আইবো নি?
ভিডিও অফ তো
অফ নি?
Yeah, very good afternoon to everybody. I welcome you all for the session 2 of day 1 for the 3-day faculty development program on civil engineering structure subjected to vibrations. Now I'll introduce the speaker for the session 2, Dr. Guruprasad YK. He completed his MTech from MSRT Bangalore and is PhD from IISc Bangalore and postdoctoral fellow from Structure Division, Department of Civil Engineering, IISc. His professional experience, he worked as an engineer in Sterling Engineering Consultancy Service. He also worked as associate professor in Department of Civil Engineering, BMSIT, and right now he's working as associate professor, Department of Civil Engineering, RIT. He has several publications in journals and conferences, both international and national conferences, around 20 numbers. Okay, his areas of research includes structural analysis and design, non-destructive testing and evaluation, repair and retrofit of structural component using FRP composites, thermal analysis of concrete and reinforcing steel, structural dynamics, microanalysis of concrete and reinforcing steel exposed to high temperature, fracture mechanics. He has won several awards. Some of them I'll just list it out. ACCE Sundaram Merit Award 2007 for best dissertation for MTech dissertation work. Student from engineering colleges of Karnataka. Okay, and he also received an award on Best Presentation Award in the Annual Student Symposium 2010. He has several affiliations, life member, affiliations against his name, Concrete Institute, life member of Indian Society of Non-Destructive Testing, associate member of in some of the journals. First one is American Concrete Institute, Structural and Material Journals, Springer Sadhana Academy Proceedings in Engineering Sciences, KCE journals. Okay. Now I'll just hand over the session to Dr. Guruprasad YK. Thank you. Yeah, that's fine.
Very good afternoon to all. Very good afternoon to all. Is my PPT visible to all? Visible to all? Yeah. Yes. Yes. Very good afternoon to all. I'm Dr. Guruprasad. Work as an associate professor in Department of Civil Engineering at Ramaiah Institute of Technology. Today's talk, I'm going to give on ductility requirements in structures subjected to earthquakes and retrofitting. In the morning today, you would have heard Professor Anand about various aspects on retrofitting and on earthquake engineering. But today, for the present session, I will be talking on more in detail on ductility requirements. I will not go into too much of mathematics because earthquake engineering and structural dynamics are subjects where we make use of a lot of mathematics to get the physics out of the problem. Now, in this case, there is an echo. One second. Okay. Can you hear me? Can the participants hear me? Can the participants hear me? Okay. So today I will be talking on ductility requirements related to earthquakes and its importance and retrofitting concepts. I would like to also put across that I would not go into too much of mathematics. I would stick to more of applications and in the form of figures which I put across in my entire PPT, such that it is more understandable to all the participants who are from a different range. It may be a professor who may be sitting across, or it may be a student too, from a BTech to an MTech level. So the contents of my presentation goes like this: sources of damages in RCC structures causing instability, irregularities in structures, RC structures because of earthquakes, the different type of irregularities which exist, concept of ductility in structures, methods of implementing ductility into a structure through the conventional methodologies during the design phase itself, strong column beam concepts and pushover analysis. These go in detail of hinge formation and ductility concepts. A case study which is going to be also be presented to you, which has been worked upon, and a capacity-based design on hinge formation and stability of a structure subjected to earthquakes, how we are going to implement the concept of weak beam and strong column concept. Adopting this, how are we going to design based on capacity-based design also I'm going to talk about. Assessment of damage in a structure and its members, adopting NDT, non-destructive testing, that is being damaged due to earthquakes, repair and retrofit measures to restore back the stability and strength in a distressed RC structures or the distressed RC member that has been damaged due to earthquakes, global and local retrofit measures. One case study of a global retrofit measure, and also a case study of a local retrofit measure which is going to be presented. Passive control techniques, that is earthquake controls in that structural controls, what we have in that passive controls I'm going to talk about, and conclusion. So first, let me talk very briefly about what is an earthquake. Many people who are working in this particular domain will be aware of it. I'm talking on a broader spectrum of all the participants who are sitting here. An earthquake is basically a disturbance which usually takes place at below the Earth's surface due to the crushing of the strata because of tectonic plate movement or due to fault movement. And because of that, waves get generated, and the waves tend to traverse from the point of the disturbance, which is also called as the focus, up to the surface of the particular Earth, where it first hits. It's called as epicenter, which is the vertical distance just above the focus. And the waves traverse from the point of the disturbance or the focus in the form of P waves, S waves, and S waves in the sense you have shear waves. P waves are called as primary waves, shear waves, and among that you have love waves and you have surface waves after the shear waves. In surface waves, you have love waves and Rayleigh waves. Surface waves are the ones which usually traverses on the surface, which tend to cause a lot of damage to the structures on top of the particular on the diagrams have been put across for your understanding. Now, basically, considering a structure, I've considered a reinforced concrete structure in this case. Basically, a reinforced concrete structure has the earth surface, basically following things. So you can see slabs and shear also. And this is subjected to a ground motion, basically earthquake. Then have a response to the earthquake, basically. It tends to undergo displacements because of the lateral force distribution across its height at various floors or story levels. Now, basically the behavior of the buildings due to earthquakes is through a inertial force action. It is, you have the earthquake force acting in one direction. Usually the basic behavior of a building is not to go along with that, but there is a inertial resistance force. As we have understood in the concept of dynamics, what we study is the excitation force is there. To counter the excitation force, we have an inertial force, we have a damping force, and we have a stiffness force. So basically, to put it across in a very simple way, there is an earthquake which acts and the building tends to react in the opposite direction such that inertial forces develop to maintain its stability. Now, what happens during an earthquake in the various components of a structure, especially in the slab and in the beams and columns? We see that there will be a set of columns which tend to go, not only a set of, most of the columns when they are subjected to lateral loads, they tend to undergo lateral deflection, as well as there will be axial loads which develop into the beams, and they too undergo, or they too beams to develop compressive stresses. In the case of an earthquake, you could see here, there is a figure here which shows a infill wall that is inside a frame. You can see the red arrows here showing the lateral loads. Here, even the beam is subjected to axial forces, and the columns are also subjected to something called as, apart from moments and axial force, the columns under also are subjected to shear, horizontal shear. So when we consider this into our earthquake resistant design, we have to consider all these forces. In a conventional non-earthquake resistant design, we usually design a column for basically axial loads and for biaxial moments. But in case of earthquake resistant design, we go for as well as axial load, biaxial moments, as well as shear. And in the case of a beam, the axial load is also taken into consideration. Now, basically for a gravity load, we have the bending moment diagram for a frame, basically. So when there is an earthquake is a random vibration, basically. It is basically a dynamic load. How do we define a dynamic load? Whose magnitude varies with time. So in this case, you would see that when there is a dynamic load, especially an earthquake acting onto a frame, there will be a to and fro motion onto the frame. So on one side, when the frame is going to sway to the right, there will be tension in some of the members, especially in the columns on one side, and when it's going to sway in the other direction to the left side, due to the to and fro motion, there is going to be reversal of stresses. You can also see this in the case of the bending moment diagram, where there is going to be the change in the moments which are taking place. So you will see the one in the center, that is for a static case, whereas you see to the right, you will see the bending moment diagram, where the variation in bending moment diagram when the structure or the frame tends to sway to and fro. Now, these are, and I would also put it on record, these are some of the particular information which I have taken from IIT Kharagpur's, to put it for a better clarity for all the audience, so that it should not just become a completely a mathematical talk, or it should not be something which makes you, which can make you comprehend much easily. Now, these are the photos of the buildings which have been damaged during the Bhuj earthquake. This has been taken from EERI reports, which has been put here. You can see that the buildings have got extensively damaged. You could see the building on the right hand top corner. The building has totally collapsed. What does this show? We have done the RCC design, but still, why haven't the buildings been able to resist the earthquake? Or why isn't it been able to withstand it? Even the previous speaker talked about it, because we can't design for an earthquake of a very large magnitude which may not occur at all, making the building even more, from a economy point of view, it would make it uneconomical. But at the same time, we have to also cater to the needs from a design point of view, such that the stability is restored. So I will be talking about that in detail in the forthcoming part of the talk. You could see here, in the first building here, you would see that the major portions which are like the staircases, the water tanks have collapsed. You would see that even the staircases have collapsed here. In one of the buildings, the one particular entire floor, all the columns have crushed and it has come down. You would see in this next forthcoming figures, you will see the shear wall, which is used as a lift wall. It has collapsed. I mean, not collapsed. I mean to say it's badly damaged, and you would see the building to the right side. You would see that the beam column joints have got separated, and in some of the cases, the entire building has collapsed because of failure of the beam column joints and also because of the failure of the columns. You would see to the bottom left corner, the columns have, the reinforcement in the columns have buckled. What does this say? There is not in detailing consideration which has been taken into effect, because they have gone into the conventional detailing, and there might have been cases of aberration in execution in the detailing during the construction practice, caused the lateral ties to be placed at a larger spacing. You can see here, basically the rebars have buckled. Why did this happen? Basically, it is a fault, or if it is taken into the conventional design, it should have resisted. We'll come across that in the forthcoming slides. Now, basically, it is called as seismo-resistant architecture. If we take this into consideration, when we design buildings, it is going to be designed based on aesthetics, because every person who gets their house to be constructed or designed would like their house to be having a certain type of aesthetics, and so are the buildings which come up in our cities too. So we see that while catering to the aesthetics requirement, we see that there are some particular irregularities which creep into the structure, which tend to cause instability in the structure when such an event of an earthquake takes place, causing instability into the structure. So let us see what are the different type of irregularities which are existing in a structure. Basically, there are 4 types: vertical irregularity, you have stiffness irregularity, mass irregularity, plan irregularity. And in plan irregularity, you have also cases where diaphragm considerations are taken, where cutouts are given in slab. I will talk about it. So you see here in this figure, it is a vertical irregularity which is considered. You see the topmost right corner figure, you will see that some of the particular beams have cantilevered. You see to the left side also, you'll see there is a upper level floating column which has been provided. So the column is not extending all the way up to the foundation below, whereas it is used for load bearing purpose. This is resting on a critical region of a cantilever. And at the bottom, if you see that, there are cases where practices are made where shear wall is not continuous up to the foundation level. These kind of errors have happened and has been considered into the construction, because there is a wrong notion that when we provide a shear wall, it's a reinforced concrete wall, it is going to give enough strength to the structure. No, it is not so. It has to go all the way up to the foundation level it should be continuous from the foundation level up to the topmost story, where we see that in some of these cases, it is not. Now, the next is strength and stiffness irregularity. That is stiffness irregularity, which I talked about. If you see this particular building here, you would see in most of our apartment buildings also, we'll see the bottommost ground, that is basement story, is usually kept open. I mean to say all around it is kept open, because for the vehicles to move around, to park the vehicles, that's fine. But you know what, this is going to cause a condition of an open story effect. Okay, so what happens in this, you would see that walls have been built into the frames, that is infill walls are built into the frames, causing enough stiffness to the frames above, whereas there are no walls at the bottom, causing lower stiffness to the basement story. So when an earthquake strikes, it's like a huge load on, it's like having a very big, a very heavy head, a very heavy head and a thin body. So what happens when you are pushed? You just fall down. The same thing happens to the building here. You would see the bottommost story here in the basement lacks stiffness, and that also corroborates to the strength. You can see here some of the buildings which have got open stories at the bottom, basement. The columns are not only sufficient to resist that particular lateral load, I mean to say the stiffness is lower in the lower story. And you can see in one of this figure to the left, the entire story has, the columns have crushed and the building has come down. The next is mass irregularity. One is vertical irregularity. The next one was stiffness. Then it's the mass irregularity. What is mass irregularity? Basically, when you are going to place mass not in the particular mode of design it should be in. For example, I'll give you an example. Practically what I have come across in our own Bangalore city, I would not like to disclose the details of the project, but I would like to tell you, most of the buildings in our country sometimes, we'll take the case in Bangalore itself. What happens, it goes for, you design a building, it goes for a sanction. It may be for a residential sanction, okay, 3 floors. But what happens, after getting the residential sanction, people also rent out some portions to commercial occupancy. So there is going to be a difference in the load of the structure, especially based on occupancy. For example, you would see that some part of the building is occupied for residential purpose. If you go by IS 875 part 2, it is 2 kilonewton per meter square. At the same time, when you go for a commercial purpose, the live load consideration changes there. According to IS 875 part 2, it goes to 4 kilonewton per meter square. It depends upon what type of commercial occupancy the person is giving. So in some cases, we have seen that places are given for storage, like a godown. In such cases, when there is going to be a differential in mass, that is in the floor loads, this is going to cause a mass irregularity. What does that, how does it affect the structure? It definitely, because the structure which is supposed to be loaded for a particular loading, and when it is overloaded at a certain story because of the limits, the various partial safety factors which is considered into design, which makes it to take the load, but still it is going to cause an instability when the earthquake is going to take place. Next, as I told you, this is again a vertical irregularity. Next comes plan irregularity. Now in plan irregularity, we have, when we don't have a structure which is symmetric in plan, it is bound to undergo a larger amount of earthquake damage. I'm talking in simple terms here. I'm not going to use very complicated terms here so that it is understandable to everyone here. Like re-entrant corners, I'm not going to talk about anything. I'm just going to say it in a very simple manner here, stating that when you are going to have a plan of your building which is not symmetric, okay, it is going to definitely undergo damage when the earthquake is going to happen. In what way? Such structures which are unsymmetric in plan are definitely going to be subjected to torsion in plan. That is twisting. The entire building gets twisted in plan. What is going to happen when the building is going to twist in plan? What you will ask me. Basically, what happens? The major elements which come under damage are your columns. The column gets, I guess all of you would have seen people washing clothes. They tend to squeeze out the water, right, by twisting the clothes. Similarly, the same torsional effect happens onto the columns, causing the columns to develop very high shear stresses in those particular portions, causing the columns to completely collapse in some cases or get damaged in a very, to a large extent. Now, at the same time, when we are going to have plan irregularity, if we are going to provide cutouts in slabs, it is called as a diaphragm discontinuity. This also is going to cause instability in the structure and causing distress in the structure when the earthquake is going to take place. At the same time, if we are going to provide walls to only 3/4 height or half the height in some structures, you would see that the stiffness of the column in between the columns, the wall which is being provided in between the columns in the frame, it is going to cause distress to the portion of the columns which are extended beyond it, beyond the particular walls. And the same thing applies for even openings, that is window openings which have been provided. I also like to put on a note here, when you are going to provide very, very large window openings, very large French windows, I don't say that you should not provide it, but a structure which has too many openings is less stiffer when compared to a structure which has the required moderate number of openings, that is windows and doors. So basically, how does the load transfer take place during the earthquake in the various components? You would see that this is the foundation level. Basically, the earthquake is taking place. It is transferring in terms of shear stresses. It transfers, and the major part which is of the earthquake load which is resisted are by the walls or by the RC shear walls. Basically, the roof will act as a diaphragm, just moving as a rigid diaphragm. Now, first of all, we need to know how flexible are our buildings. Okay, so when an earthquake takes place, what happens? Basically, it is like pulling the structure. It's just what you say, giving you a ideology of just pulling the structure and leaving it, how it's going to vibrate. Now, based on the height of the structure, you can confer upon how much would be the damage. For example, coming from the point of dynamics, talking from the point of dynamics, a single story building has a time period of 5 seconds, whereas a medium low story building has 0.4 seconds, whereas that of a 15-story building has 1 second as the time period. Elevated water tank, which has a huge mass on top, has 4 seconds, and that of a chimney 2 seconds, and the suspension bridge 6 seconds. You'll ask me, how does it matter? So here, the time period actually refers to how stiff is your structure, and the more it's going to get too flexible. I mean to say, let me tell you, most of the structures which stand on Mother Earth are cantilevered. They are basically cantilevers. It is the foundation which is fixed. It is fixed at the bottom. It is presumed to be fixed. It's actually not fixed, because when you take soil structure interaction, you can't really call it fixed. But conventionally, we call it fixed at the bottom, and it is free on top. So in such kind of structures, it's basically a cantilever. So larger the height, larger would be the displacements, and so would the stiffness also come down comparatively. So at the same time, you would see that when there is a strong earthquake which takes place, a strong motion, there is a peak ground acceleration. The peak ground acceleration is very high in the earthquake. In such a case, what happens to low-rise structures and high-rise structures? This is a typical figure which I put here so that you can get an idea about it. Basically, I'm talking about the basics of earthquake engineering. Now, coming to the ductility in structures. The previous speaker also talked about this. Here, I would be also going in detail about it. Basically, what is ductility? Let us define it. Get a clear picture of it. Ductility describes, it means to say what the amount of deformation a structural component or a structure undergoes when it is subjected to a certain load without failing. That is important. This is called as ductility. Now, a structure or a material or a component is said to be brittle when it cannot undergo large deformation or large displacement for the same applied load. It may break. For example, glass is brittle. Whereas concrete is not, many people say concrete is brittle, but it is not brittle, it is quasi-brittle, because it has a post-peak response. It has a softening part of the curve. So if you take cast iron, you take glass, they're all brittle materials which will just undergo failure without giving any kind of indication, or suddenly they fail. Whereas we have to design our structures such that they are ductile enough and they do not fail in that manner, because we are going to make use of so many materials to be put together to erect the structure, and after that the structure should perform in such kind of eventualities like an earthquake. So basically there are 3 types of ductility in a structure. Basically the main ones: material ductility, section ductility, and structure ductility. Let's see what they are. Material ductility, the first thing which goes into making the structure. What is a structure made up of? It is made up of materials, right? So the material what we use should have a certain amount of, it has a certain behavior. So the type of materials which we use also reflects upon the the behavior of the material reflects upon the total structure's behavior when it is subjected to loading, be it gravity or lateral loading. So basically, how to make the material or the structure ductile, it depends upon the material. So here we see that steel, we make use of reinforcing steel here. I'm talking in the case of reinforced concrete. Steel is a ductile material. In that we had mild steel and high strength steel. At present, you don't get Fe250 for rebars at the moment in any of the outlets. It is Fe500 which you get. So it's high strength steel. It is ductile comparatively to concrete. So you have unconfined concrete, means plain cement concrete which we have, which is not ductile. How to make that concrete ductile? By providing confining reinforcement to the concrete, we make the concrete to be ductile. What do you mean by ductile? It can undergo larger deformation. In what? Basically, it's in compression, because concrete is good in compression and weak in tension. So next, it's the section ductility. What do you mean by section ductility? Here, you have two cases of ductility. One is rotational ductility and one you have curvature ductility. So what is rotational ductility? For example, you are going to have a beam, a simply supported beam which is subjected to a point load in the center. I'm sorry, I'm not able to use a whiteboard here, or else I would have just put it across and showed it here. So do I have that? No, it's okay. I have a simply supported beam subjected to a point load in the center. So what happens? The beam deflects to form a curvature. At the supports, the beam tends to have rotations or slopes. They are called as rotational ductility. How much each section of the beam, if you're going to draw a tangent to the elastic curve of the beam at each point coming up to the center, you are going to get some slopes. Yeah, it is basically rotations. So if that rotation is going to be close to the yielding of the material based on the moment which is going to cause the yielding of the material of the beam, it is called as rotational ductility, which takes into consideration the yield moment and the maximum plastic hinge rotation. I will tell you about what is plastic hinge. I'll come to it in detail. Plastic hinge is where the entire particular material at that point in that particular structural component, take the case of a beam, has completely yielded or plastified. Okay, so there is no more resistance there, but the material just gives way and the particular structural component just rotates. Okay, so this is rotational ductility. The next is curvature ductility. Curvature ductility, you would see this particular figure on top. You have the bending moment, the moment which is acting, and the curvature which has taken place. You see here, you see the curvature which the beam has deflected and subtended. That is phi. So the curvature which is related to when the yielding of the material and the maximum curvature. So the ratio of the maximum curvature to the yield curvature is what which is going to give me curvature ductility. And here the rotational ductility is measured as 1 plus the rotation maximum plastic hinge rotation to the yield rotation. Especially theta y here, which is given is that for a beam. It applies for a beam here. That's why I would put it on. I would like to inform you. Next comes the structure ductility. Here, in the case of a structure ductility, I have a building. You see here, I have a building here. It's a frame building with infill walls, and it is subjected to a lateral load, and it is going to undergo some lateral load H, a horizontal load H, and it is going to undergo a lateral displacement delta. Okay, so how much is this value of delta going to be such that the building is not going to fail or it is not going to collapse? That will give you an idea about how good is the ductility. You will see this graph here. How good is this ductility? If the delta is large, comparatively large, I would like to use the word, and the structure undergoes deformation without undergoing collapse or failure, then it is called as a ductile structure. What is this whole concept of ductility we go on talking about? Why should the structure be ductile? Why should it be designed as ductile design? Is the main reason in earthquake resistant design. I would use the word resistant design. It means to say that when such an event like an earthquake takes place, the structure, even if it is going to get deformed, it is not going to collapse. There is enough room for people to escape out. That is most important. If you are going to make the design in such a manner that you are going to make it brittle, the structure is going to be designed in a brittle manner. I mean to say is that it cannot undergo a large deformation, a comparatively larger deformation, and collapses, causing life loss, then it is not a ductile structure. So here the ductility of each and every structural component in the building also contributes to the entire structural ductility, that of a column and a beam, okay, and inclusion of shear wall too, which I'm going to talk about. So you can see here that a structure which can undergo a larger lateral displacement. It's here, you can see on the y-axis it's a lateral force, and the deformation is definitely the lateral deformation is a good, it has good ductility, whereas a structure which has moderate or medium ductile and a structure which has lesser deformability index, we call it as, it's called as a poor ductile, which has poor ductility. Here, this structure ductility is measured as the maximum displacement by the yield displacement. Here you would also see that there is some equations which have been put here. What are they? You see a plane frame, a portal frame which has been shown here with a lateral load. You'd see that Kc is nothing but the stiffness of the column and Kb is the stiffness of the beam. So mu m would be the ductility of the beam. I would repeat, mu m, which is shown in this equation, is the ductility of the beam. Thereby, that also through that we tend to measure or determine the structure ductility. Here you could see that the structure ductility depends on the ratio of the stiffness of the beam to the stiffness of the column. And it is seen that the ductility tends to, there is a variation in the ductility as you see in the graph here. Now, how do I enhance the ductility of the structure which I am going to design? That is through basically which we already have in our IS codal provisions. Based on IS 13920, we have our conventional methodologies, which is called as ductile detailing and design through IS 1893 in conjunction with IS 1893 and IS 13920 2016 codes, which have been the latest revised codes. Here you see that according to 13920 ductile detailing, it says that at least 50% of the steel, whatever you provide in the tension zone, should also be present in the compression zone too. That's what it says. I'm not going to read out each and every point from this. I'm going to explain point to point so that it makes you clear. Now, here there is also a lot of importance given to the lateral, or in the case of a beam, the stirrup reinforcement, and in the column, there is a lot of importance given to the lateral tie reinforcement in columns. So it says here that there should be a 135 degrees hook should be provided in this particular manner as per IS 13920. So, and this is taken as the confining reinforcement. Basically, we see that, you see this figure, you see that the lateral, the stirrups are placed at a lesser spacing close to the supports, and it is placed at a larger distance in the span region. The reason being that due to a larger amount of shear which takes place at the particular supports, to take care of that, and due to reversal of stresses and shears too, this particular type of detailing is done such that the beam should not fail in shear at the supports, and there should be a ductile behavior, and it should show enough deformation, showing it as a warning for people even though it is going to undergo damage without collapse. I would not go into the details, too many details of the ductile detailing. It is available in IS 1392/2016, whereas this particular spacing of the stirrups to be provided is at a distance of 2 times the effective depth from the face of the columns, and it is placed such that you tend to have enough shear resistance at the supports. And at the same time, I would also like to put across that in case when we are going to have laps, when we are going to have splices in reinforced beams or in columns, we are going to provide, especially the lateral reinforcement in the case of a beam, that is stirrups, are provided at a spacing not more than 150 mm in the zone of the lapping zone, to see to it that there is no opening of the lap. And one more thing I would like to put in, mention here, you never provide a lap in the central span zone for a beam. At the same time, you never provide a lap exactly at the support into the column. The reason is it can open up at the column due to high shear, due to dowel action, it can open up. And when you are going to provide a lap in the central portion of the beam, that is mid-span of the beam, it is going to have a large moment acting there, causing there is going to be, the tension is going to be highest at that particular point, especially at the bottom or in the tension zones. The lap can open up. So where do I provide a lap? The lap should be provided in the beam. If the beam is having an effective span of L, it should be provided at L/3 or L/4 distance from the face of the support as far as possible. But in practical site consideration, sometimes when this kind of a situation comes up where the lap comes towards the center, not exactly at the center, close to or a little away from in the span region of the beam, there should be stirrups which should be provided, and the spacing should be not more than 150 mm in that zone. Now, coming to the case of columns, we just saw in that previous figure where it was damaged due to earthquake. I also told that the columns also undergo shear when the building is subjected to an earthquake. So here the lateral ties also act as confinement reinforcement, also help in taking the shear, lateral shear, which is going to come onto the particular columns in the structure. So here we see that according to the same ductile detailing as per IS 13920, the lateral spacing of the ties in columns should be placed closely near the joints. And also would like to put on record here, it has not been shown in this figure, but I would like to say that even at the beam column joint, you have to provide a minimum number of lateral ties to give a confining effect in the beam column joint, which is never done for nominal. I'm going to show you that in the next forthcoming slide, which is never done in conventional detailing. So you see here that the lateral ties are placed just like in a beam. It's like you take the beam which was horizontal here, you take it and put it vertical. It will the same type, I would not say it's the same. On the same front, you would see that the lateral spacing of the lateral ties are closely spaced near the supports or near the joints, and there is going to be additional lateral ties provided inside the joint. The details of the spacing of the stirrups and that of the reinforcement, I'm not going to get into it because you will get all these details in IS 13920. But basically, this is the ductile detailing which we need to adopt in construction when we are going for a earthquake resistant design of structures in reinforced concrete. Now, as I just told you here, we would see that in a beam column joint, basically there is going to be what? Basically, the load is going to be the moment which is going to, very large moment which is going to take place, is going to get transferred in the form of bond stresses and diagonal compression and tension. So I would like to show you this needs to be resisted. See, this rebars can get pulled out and you are going to develop a large shear too. In such cases, you would see that in this detailing, you see that of a formwork which I put it across here for ductile detailing. You'd see that the first figure on top, you'll see the lateral ties in the beam, in the column, and in the successive A, that is in A, you'll see it on top. B, you'll see the lateral ties being placed at the beam column joint inside. You can see it here. The red ones are the lateral ties provided at the joint too. The basic reason is to provide confinement. Now, the next point comes here. I wanted to correlate this, the previous slide to this. You see that I told you that what happens here, there is bond stresses which is developed, very high bond stresses. There is possibility of the reinforcement to get pulled out. So in such cases, we have to provide adequate anchorage in the reinforcement at the beam column joints such that the beam column joints do not fail as we saw in the previous figures. The reason for this is that it causes an interlock, and therefore in case there is the joint gets damaged also, the steel in the, especially the steel can yield but may not rupture. But at the same time, if you have given a very small development length, there is possibility that this reinforcement can get pulled out and the beam can come out as we saw in this figure here. I would like to show you here. You see this beam column joint completely out. You see this, the beam column joints have completely disengaged. That should not happen. Now, I'm sorry, I had to go back and show you. The next is, how do I instill ductility on a structure basis? As I told you, structure ductility. By including or considering shear wall into the design. This is for new designs. When you're going to design the building newly, you're going to construct it newly, consider shear walls. What do shear walls do? They take in plane shear. They take in plane shear, making the building more laterally stable. Now, coming to the concept of beam column, strong column, weak beam concept. Many of you would have heard this, and in the previous talk also. I would like to put it, I would like to tell here is that this concept is important because the concept of beam column joint is which makes the, especially the damage which is going to take place at the beam column joint, is which is going to determine that particular portion of the structure is going to be stable or not. So basically, the column of strong column weak beam is which has to be considered. Now, what do you mean by strong column weak beam? Do you mean to say that someone may put a question, I design the beam to be weak, I'll make it weak, and I'll design the column to be strong? No. You consider the same loads which are going to act on the structure from the stability point of view, from limit state of serviceability, limit state of collapse point of views, and still you're going to make the beam to be more ductile when compared to the column. What do you mean by that? The next point comes, you're going to allow plastic hinges to form only in the beams at the beam ends. Okay, so such that there is going to be rotations which take place at the beam ends, causing the energy to be dissipated. Like as Professor Anand spoke, he talked about energy ductility also, which I have not put here for certain reason. There it is the energy ductility which is going to matter. I think I'm getting some questions. Should beam reinforcement be induced inside column for ductility design? I'll come to all these questions. I will answer all your questions. I'll come to that. Beam reinforcement will go in as I'll come to it. I'll address all the questions later. I have a huge amount of slides which is there, but I need to complete with that, please. That's why I'm just running through. You would see here this concept of strong column weak beam. I'm going to run you into pushover analysis. Why do we take this strong column weak beam concept? I'm going to take you into pushover analysis. We are just not going to just talk about strong column weak beam and just be done. No, I'm going to take you how you design also to make you decide where you are going to allow the hinge formation to take place from a design point of view as a designer. You got it? From earthquake engineering point of view. That is which we have to design, which we have to decide, not allow the structure to develop the hinges where it should when the earthquake takes place, and then it can happen anywhere. So from an analysis and design point of view, you do what you say, a calculated study and design, analysis and design, and locate where are the zones where the plastic hinges form, and you design it accordingly. So here we see that which is desirable in the earthquake resistant design, that is strong column, weak beam. You see that at the beam ends the hinges have developed. Okay, this is a desirable plastic mechanism. You see the one below, all the three below, they are undesirable plastic mechanisms. If there is going to be a plastic hinge developed at the in the columns just below the beam column joint or just above the beam column foundation joint, what is going to happen? It is just going to rotate. The entire structure will come down, or one portion of the structure. You see the one to the left or right side, that is figure B, undesirable. It will just come down like a mechanism, which is not desirable. It is like, let me give you an example from a medical point of view. I'm sorry. See, because if our entire body is a structure, and every single joint is somewhere, it is a two-dimensional hinge or a particular hinge in a certain direction. That is, if you take the ball and socket joint, so they are hinges. Now, if we damage our collarbone, which represents in the form of a beam, not much is going to happen. But if I'm going to damage my knee, a hinge kind of a damage which forms on my knee, what's going to happen to me? I'm going to fall down. That is which is going to happen to the structure. Now, you see here that at the beam column joints, the hinges are preferable in the beam region. Now, the next thing comes methods of seismic evaluation, earthquake evaluation. It should be, there are two types, qualitative methods and analytical methods. Qualitative methods and analytical methods. In qualitative methods, what do? Basically, we go from a point of view of, it's basically, we have to go to the site and do the condition assessment, visual inspection, and non-destructive testing. Analytical methods are CD method, which we have, pushover analysis, inelastic, time history methods. Now, these things, how do? I collect all the data of the structure from the site. If there is no data available in the form of already existing plan or structural drawings, they are not available. We have to go to the site, do the measurements, what is the span, base span, story height, and what may be the particular type of reinforcement which has gone in. That use NDT methods also, and find out what would be the bar diameter, and at least there should be some kind of documentation from that, and you erect a computer model and run the analysis for that particular and simulate the earthquake scenario and see. So these come under the analytical methods. So I'm going to, in this talk, because this is a vast topic, I'm going to talk upon pushover analysis. I have considered pushover analysis because just now I talked about beam column joint and strong column weak beam concept. So what is pushover analysis? Basically, at present, what we do is a linear elastic analysis. So for seismic design, so, and we do a ductile design for it. We do ductile detailing according to IS 13920. Okay. So I'm talking about practical stuff which is also carried out in designs. Okay. I'm not just talking from a theoretical point of view. So what we do is that when we take the elastic analysis into consideration, you take the softwares like ETAB, STAD, or SAP. They make use of response spectrum method. Okay. Or you do a hand calculation by equivalent static method. Okay, I'm not going to get into that because that is part of structural dynamics and earthquake resistant analysis too. But that would take some time. But I wanted to mention that here. In that case, you are considering the material to be in elastic regime, which is not true, which never happens so in an earthquake. When you see when an earthquake takes place, a moderate earthquake also, you will see some. I'm not saying a low intensity earthquake. I mean to say a moderate intensity earthquake of around 5.5 to 5.7, 5.8. You would see some amount of damage which would be there. Okay. So on Richter scale, I mean to say on Richter scale of around 5.5 to 5.7. So you would see that from 5 and above, less than 6. I would not say you would see cracks developed in concrete members. Once the crack develops, it's a structural crack. It is definitely crossed the one particular material, be it concrete or the steel has yielded, it has crossed the elastic limit. So in that case, what do? Do you mean to say the stiffness of the structure will remain the same? No. It will never be the original stiffness, what had been there earlier. So in this case, what is pushover analysis? Pushover analysis is a nonlinear analysis procedure to estimate the strength capacity of a structure beyond its limit state up to its ultimate strength. So basically what it does, it can help to demonstrate how progressive failure in a building can take place and identify the mode of final failure. You can find out where the particular plastic hinge formations can take place. You can find out, okay, this portion, this particular point can get damaged. It may be that some places you have provided very stout columns, some places where you have provided very slender columns. Today's date, what we see in and around Bangalore is that we see columns of 6 inches by 1 feet, 6 inches, 150 mm. That is what we see, which is we have to really question that we have to follow the code IS 13920. What is the minimum width it says? Are we following it or are we following the provisions? No. In such cases, if you have really, if such a structure has got damaged, you do the modeling of that and see where it might have got damaged or where it can get damaged to. I mean to see as a predictive precursor. So then next you can also find out what would be the deficiencies in the structure which you are already going to design. I put PA here for pushover analysis as a short form, please. And this pushover analysis can be also used as a analysis for retrofitting purpose also. How do you say that, you'll ask me. Now you already have an existing structure. Okay, it's a hospital building. I'm going to talk about that. We have some of the hospital buildings which have been retrofitted for earthquakes. I will just talk about that also, which are existing in India using other modalities. I'll show you that. I want to retrofit it. It is in a earthquake zone of maybe 4 or 5. It's already existing. I need to restore that hospital now. You take the case of COVID condition only. God forbid no earthquake takes place now. But I mean to say that what do I do? So in that case, you model, you have all the details of the building, of the structure, including the architectural plan, structural, general arrangement of beams and slabs, that is the structural plans, foundation details, everything you have, soil data, everything, what type of soil on which it has been built on also, okay. What do? You recreate that model, you do a pushover analysis and find out where may be the possible zones of hinge formations which can take place. So you can do a predictive analysis to see, and you can scrutinize on retrofitting options. Next, pushover analysis is always carried the convention out after as a seismic analysis. You take ETABS or STAD. What do? Or any other software to enter what is the zone factor, you will enter importance factor, you will response reduction factor, all this you are going to enter. Okay, SA by G based on the type of soil also. Okay, so you will enter and you do the analysis. Refine the design, I'm sorry. You are going to do the seismic design based on that. Then you'll ask me a question. Should I sit and do the design twice? No. When you do the analysis first, using seismic analysis, the normal seismic analysis which you carry out, after that you do this pushover analysis to find out what may be the possible zones where the slide here. I am not going to read word to word. The reason is that I thought of putting the concept across clearly so that it is clear to you all. Now, for a new building, this pushover analysis, as I told you, is the second stage. As the first stage is conventional. Now, what you can do with this is that you can do modification to your design. Okay, how? You can identify the zones in the model. I'm going to show across to you the hinges where it is going to form. And how do I do this? You use any of these particular packages which are available. STAD, SAP 2000, ETABS, MIDAS, okay, if you have the computational capacity, computational space, and also the type of environment, you can make use of FEA softwares like Abacus, ANSYS. You can model the entire structure in 3D. Definitely, this is also in 3D, but the thing is that in ETAB, SAP, and StatPro, you will see that all the particular. Whereas you take it into these FEA softwares, you can model it in 3D. The beam column cross sections also you can design, you can model it as is. So from this, you will be able to get the hinge location formation, the location where the hinge formations can take place. Now, what are the different type of hinges that can develop? I'm going to go a little fast, please. If you don't, I would take your permission for that, because I have a lot more to cover on retrofitting and capacity-based design and all that. So that's why I take your permission for that. See, basically, we have three types of hinges: flexural hinge, shear hinge, and axial hinge. You'll ask me, basically, these hinges are supposed to develop at the beam column ends only, not at the joint. If it happens at the joint, it will form a mechanism and the whole thing will come down. But basically, it is expected to happen at the beam ends. And the hinge should be at a distance of at least 5% of the length of the beam from the support face. I would like to put it on, I would like to inform you. I have not put it here, so I'm just telling that here. And one more thing I would like to tell you, you'll ask what is an axial hinge. You have walls, right? You have infill walls. When the walls are going to undergo compression, they too can crush, as I showed you in the slides earlier, infill walls. So there an axial hinge forms because of an axial strut action. Okay. So basically in the pushover analysis, we consider the moment versus rotation of the hinge, okay, wherever the hinge formation happens. And this entire thing is represented as a curve. And the portion AB represents the linear range, unloaded state, or it is in the elastic range, basically. It is the portion BC which we take into consideration, which we are going to break it up into different particular what you say zones, I can say, in the analysis. What is that? So here IO is the immediate occupancy, LS is called as life safety, and CP is collapse prevention. What is that? Let us see. See here what happens in this case. If you are going to have your structure in IO, within this IO zone, it is intermediate occupancy. There is going to be some amount of damage. Yes, it is not to a very large extent. And in LS, there is moderate to a larger amount of damage, but there is no life loss. It should not allow for collapse. That's what it means. And CP is the ultimate point. It should not reach to this point such that it is going to cause collapse. Okay. So we have to look into this, and when you are going to use any of these softwares, let me tell you, it is going to provide you the hinge in a certain legend of colors, if it is in IO, LS, or CP, or whatever range. So it should be within CP. If it goes to red, the red zone, it is gone beyond it, that is beyond CP. That is, after the point of CP, it is definitely going to collapse. I'm just going to go a little fast. See, you will see the real curvature, moment curvature curve, which is actually a real life scenario. You'll get it in the form of, this is an real life moment curvature curve, which you get it in blue, and this is the idealized. So I would like to put across, I'll go a little fast here. So basically pushover curve, which is what you are going to develop here. So how do you develop that with respect to base shear? What is base shear? It is the shear which is acting at the base of the particular building, that is computed from the horizontal acceleration coefficient AH, which is given in IS 1893 2016, based on considering the zone, importance factor, response reduction factor. Means what kind of a frame it is. Is it an ordinary moment resisting frame or a special moment resisting frame, that of like a ductile detailing which is done, and also the type of soil that goes on the spectral acceleration to G, that is a ratio of SA by G, we call it, with respect to that, and the rooftop displacement, which is considered. With respect to this, you make your pushover curve. So what do you do with this? With this pushover curve, I would like to go forward a little. What are the effects of torsion on beam column joint? I will come to that later. I'll answer all your questions later. Okay, please kindly bear with me. Let me finish up with this talk. So here, SA is the spectral acceleration and SD is the spectral displacement, which we call it the maximum displacement the structure it undergoes. Peak, we call it as peak ground acceleration, and we have peak ground displacement also. But SD is the spectral displacement. Here, as I just explained to you, SA is the spectral acceleration and SD is the spectral displacement, and you'll have spectral velocity also, SV. Okay, I don't want to get into that right now. I wanted to explain all this, but I would like to say that now I want to put it, I'll go a little faster. I'll take up questions later on this. If you have, I'll come to it. We developed this pushover curve SA by SD based on ATC 40 and FEMA 440. What is that which we are going to get from this? I'll just come to it. From this, we are going to come to a what would be the where would be the plastic formation. So there are two types of pushover and here existing, that is displacement coefficient method and capacity spectrum method. Okay, so basically what is done even in our softwares, we go with displacement coefficient method. Okay, so here I would very briefly talk about it. What is displacement coefficient method? It estimates the target displacement prior to the analysis to which the model has to be pushed. It means to say what? You predefine the roof displacement in this. Okay, basically you are going to predefine the roof displacement. How? I'll tell you that. You are going to define the roof displacement, and up to that is how analytically you're going to do the calculation in the software. And due to that, it's like F is equal to K delta. You are going to give the displacement. You are going to develop what are the forces which are developed in the members. That is forces and stresses. And from that you get to know where would be the hinge formations which would take place. Okay, this is based on displacement coefficient method. Capacity spectrum method is the analysis is done at each point, that is on the pushover curve, and it is consecutively checked whether the SA by SAD at that particular point meets. It is more of an iterative process in this. Okay, so basically the response spectrum curve is reduced by a reduction factor in this case. So basically, if you go to response spectrum method, Dr. Guruprasad sir will be talking about it tomorrow. I would that's why I didn't want to talk about it here. Reduced by a reduction factor. That is what is done in CSM. I would put it in short here. This can go on length and we can go on talking. So I would like to put it here that basically this is the response spectrum which is considered according to ATC 40 for pushover analysis. So you take 2.5 as an SA by G. Whereas in our Indian code IS 1893 also we consider this. Just now I talked about the horizontal acceleration coefficient z by 2 I by r into SA by G is what which is considered for pushover analysis too. For pushover analysis also you have to give the zone factor I r SA by G also for into the input when you are doing it, let it be in SAP or in ETABS. Okay, so I would just skip this for the moment and I will like to show you a case study which I have carried out. I worked with my students to just show you this, a building which is of a commercial, it's a commercial building where M35 grade concrete was used for columns and M25 grade was used for beams and slabs and shear and M35 also was used for shear walls too. For a live load of 4 kilonewton per meter square was adopted, and this was the pushover. This is the particular model which was considered. It was a building. You'd see that without the shear wall, when it was carried out, the analysis was carried out, we developed hinges which are beyond this point. I just like to come here to this particular, I'm sorry, the legend is not here. I would show you that, yes, we have B, C, D, E in that curve which I just showed you on the pushover curve. This showed that without the shear wall, there are many plastic hinges that were formed on the upper levels of the structure too. So the building is not really stable. See, let me tell you, the legend there and here is different. The one beyond D is in pink and red. It means to say that these hinges have already formed, which are going to allow a mechanism to happen. It means to say that this particular structure is going to collapse. That's what it says. And this analysis was carried out in E-tabs, let me inform you. And when inclusion of a single shear wall, it made the hinges that developed into the particular structure which was subjected to an earthquake. This is a seismic analysis through the pushover analysis. Let me say it is in zone 4 and soil type 2. Okay. It made the particular hinges to jump from the pink zone to the green zone just by inclusion of a shear wall. You may think this is just an analysis. Actually, we have done this for, I would not like to say for a particular project. We just wanted to do, they had asked us for a assessment. So based on that, this has been done and given to them, is it safe or not? That is the portion, you would see that there is an extended portion on top. The building had to be erected for an extended portion on top, if you could see here, the portion which is projected up. And that is, it has totally 1, 2, 3, 4, 5, 12 stories. So up to 5 stories they had. The 6th story was already present. They wanted to put another 5 more stories actually. For that, they wanted an analysis. So they wanted to know it's safe or not. And it was not, it was in an earthquake zone. So it was being done to show this. I wanted to just put this on record to show you when you do this in the particular, packages, you will get an idea about is it safe or not. You would see some part of the structure, no plastic hinge formation has taken place. In this particular case where the shear wall has been introduced. Actually, that building didn't have a shear wall. They had floated, I'm sorry to say this, but on recording, right? Okay, they didn't have a, lift wall, which was a shear wall, which is supposed to be there as an RCC wall, as many, I guess many would agree that even in today's buildings which have been raised beyond 3 floors where the lift core is provided, sometimes there is a frame structure which has been constructed and there are masonry walls which is built and the lift is provided in that. I'm telling practical scenario, okay? And RC wall is not provided. That was the same fate in this building. Let me tell you that. That is why no shear wall was considered. We did this analysis. Okay, I would just like to run through capacity-based design. Now I would like to just say, because I have less time, I would like to say that, see, you see these plastic hinges have formed, right? I introduced one particular shear wall here and this building has got green. That is, they are within intermediate or in between intermediate or lesser than that damaged hinge zones. Now, if I have to take this into consideration for design, what do? I have to consider the design such that I make the design in such a way that reinforcement is provided in such a way that hinge formations takes place at the beam ends. And there is no hinge formations which takes place in the columns. This comes under capacity-based design. So what do you mean by that? You see this figure here. I would run through it a little fast. You would see the M naught R1, MU R1, M naught R2, MU R2 are the design moments of the over and under columns. Means the columns which are above the particular joint and the beam column joint, and the column which is below the beam column joint at a joint, that is taking into account the axial load. ML R1, MR R1, ML R2 and MR R2 are the resisting moments of left and right beams. What do you mean by resisting moments? It is called as a moment of resistance of the beams. It is a limiting moment of resistance of the beams. Let me put it here. Okay. So based on this, we are going to consider something called as what I'm going to call it as moment consider this moment magnification factor based on I have the moment in the column which is above the joint, below the joint. It should be greater than or equal to a factor gamma RD, I'll tell you what it is, into the mod of. The mod of means you can have a positive or negative moment. So based on that, your moment of resistance of the beam to the left and to the right of the joint. I'm sorry. So this should be greater than that. So if it is not greater, it is as simple as this. The moments in the columns, the addition of moments of the columns above the joints, okay, should be greater than a factor into the moment of addition of the moment of resistance of the beams to the left of the joint and the right of the joint. Okay, when you take that ratio, you should not get it less than one particular value. Okay, let me put it now because there is dearth of time. I have to tell you in this manner so that you get an idea about it. It is called as this gamma RD is called as an overstrength factor for strain hardening, which is taken. It is usually taken as 1.35 according to Eurocode 8, which is we also take it into consideration for our analysis. So from this point, we do this capacity based design such that if I'm going to develop a column, if the moments in the column that are developed are much lesser, like you see this here, 202.6 is the moment which is developed, moment of resistance of the beam, and the top column moment is 188. It is less than that of the moment of the beam. So the column can definitely develop a plastic hinge. So what do? I'm telling in a very simple sense, I'm going to multiply this particular through a calculation procedure. I'm going to multiply this particular moment of the column by a moment magnification factor to enhance the moment such that that reflects into the calculation of the area of reinforcement into the column. And the beam, you're going to keep it same so that it is going to be more of a strong column weak beam concept. See, I'm just going to run through this. See, you see here, I'm going to put here, I have this is an analysis which is carried out. This is a frame which is taken into consideration. The analysis which is carried out, and you see the axial load in the column moments, and this is for that of the columns, for all the columns, 1, 2, 3, 4, 1 to 12 columns. And these are the moment of resistance for the beams at the ends. Okay, you are going to take this into consideration, and what you are going to do, you are going to find what are the areas of reinforcements in the beams first. Okay, then after this, what you are going to do, you are going to do an analysis capacity based design for this to check which are the columns which are deficient or which have a lower moments when compared to the beams, and you are going to do the moment determination of moment magnification factors for all the joints. Okay, and once you find out one of the columns, for example, you see seismic direction 2, joint number 1, column, that is column 14, you see that the moment magnification is not okay. I'm going to multiply it by that, and I'm going to have a moment magnification factor. I'm have to multiply the column moments with that particular factor and enhance the moment capacity such that it reflects into the design here. How? You see that here? You see the column numbers. I'm going a little fast, please. I'm sorry, because of the time restraint. I have the column sizes. I'm not going to touch the column sizes. The column sizes would be determined based on the axial load consideration, basically, and the reinforcement is going to be determined based on the moments. Okay, so basically, even the axial load is also taken into consideration. You'll get the percentage steel. From this, you also not only do with the moments, you are also going to, from that moments which you have calculated after considering the moment magnification factor, you also have to consider okay, which come into picture. So you do the lateral calculation of the shear on the columns, and you are also going to design the lateral tie spacing. Okay, sorry, there is 13920 1993. It's not 1993. It's 2016, which you have to use. It's I've taken it from Manish Shirkande because that thing has to be updated. Please, this is what I would like to put it on record here. So you have to take the moment as well as the shear into consideration, and you are going to design the what? the lateral ties into the columns also, based on shear consideration. Please mind you, for the columns it's based on shear consideration. So you see in the previous case you have 8 mm, this goes into 10 mm. And here after you do that, you do the ductile detailing completely based on your capacity based design, such that you allow the hinge formations to take place only in the beam. Now I would go a little fast here. I would also ask the organizers as well as the participants, if you can please give me another 5 minutes more. I will just be done with this presentation. I have to show you a little more. Now coming to the retrofit option, coming to the case of retrofitting. What is retrofitting? We are going to enhance the load carrying capacity of a already existing structure for any enhancement for its loads that are going to act on it, or we are going to restore a damaged structure to its actual capacity, load carrying capacity, or beyond it. Now these retrofit techniques are of two types, global or local. What do you mean global? As in a structure as whole. In global means adding new shear walls, infill walls, adding bracings, thickening the, giving a larger thickness to the walls, mass reduction in stories, supplemental damping and base isolation. That's what I'm going to talk about later. And local retrofitting is basically RC jacketing. You're going to, local means what? You're going to attack only the members, beams, columns, slabs, foundations, which I'm going to show you very quickly. Jacketing of beams, jacketing of columns, jacketing of beam column joints, strengthening of individual footings. Jacketing can be RC jacketing or carbon fiber reinforced polymers, which can be used. CFRP, carbon fiber reinforced polymers, or glass fiber reinforced polymers, which you can adopt. So damage assessment first. Before we go into retrofitting, we have to do a damage assessment. Most important thing. The various type of damage assessment, assessments are ultrasonic pulse, rebound hammer, acoustic emission, semi-destructive is core test, as well as through half cell and carbonation test. I will just briefly run through that. You see that non-destructive testing using ultrasonic pulse velocity is done to know what is the existing quality of concrete, and also to an extent what is the dynamic Young's modulus for concrete whose strength is not greater than M25. Because you go to high strength concrete, the density will not very much, you will not get much variation in E. That is what I would like to put it across. So these are the non-destructive testing: ultrasonic pulse, rebound hammer. Rebound hammer gives you the surface hardness of the particular concrete to know what is the hardness level it has attained, and that in today's date you have the latest type, which you have the digital ones, which give you the compressive strength also. But you have to do all of them. You can't just do one of them. Then half cell, which is used for corrosion detection, and you also adopt what you call carbonation test to know what is the amount of concrete which has got carbonated, which directly is related to is related to corrosion. Actually, the more the particular concrete is carbonated, your steel inside can get corroded. This is a case of a project which I worked with one of a senior, a senior design person in Bangalore. It's a project here in Bangalore itself, which we have done the assessment. So, and also take the core test. You can see a photo here, a core test taken out of the foundation footing to check what is the in situ strength of concrete. This is not non-destructive, it's semi-destructive. So you see here one more cover meter is used here. Now I just told you, when you don't have any details of the structure, how do I know what is the reinforcement which is there inside a structure which has damage due to an earthquake or whatever? Use cover meter, or it is called as a proformeter, which will give you the lateral, the spacing of the reinforcement as well as an average diameter which has been provided, and also the cover. After you do all this, you do a condition assessment. You come to a conclusion: is the particular structure fit enough for retrofitting or repair or not? You do the repair or retrofitting only when the damage is within repairable limits. And also you have to do the cost effective analysis to see that how much is the retrofit going to cost you compared to a new construction. Usually the retrofit will be cheaper when the damage is within repairable limits. Okay, this you have to keep it in mind. That's why I put it in red. You can't take a structure which has got damage like this. I would like to put it on record here. You can't take a structure which has fallen down like this and I will retrofit it. You can't put quick fix and put it back. That's not possible. So what I mean to say is that you have to assess if the damage is within what is the percentage of damage it has undergone. That you have to do an assessment. The next. Now the materials which are adopted for retrofit are epoxies, FRP, carbon, CFRP, GFRP, cement based mortars with epoxy in it, epoxy to bond old and new concrete, especially you have in post rock itself you get Nitobond EP which you get, and also you get chemicals to bond concrete and new steel also where you have to drill in. So I will just show you very quick photographs here where you will see carbon fiber RC jacketing done to columns which have been damaged, CFRP damage where the CFRP repair also has been done. You can see here RC jacketing which has been done. This is for RC jacketing in the case of a flat slab also. Carbon fiber reinforced, what is say, retrofitting. This is the retrofit of a footing. You can see here where additional reinforcement is drilled in and it is welded to the existing reinforcement and extra mat is provided to increase its capacity. These are for steel plate. You see shear walls being erected, new shear walls. Now I mean to say as a retrofit measure for earthquake resistance. Already the structure has been built. You see this is an already existing new structure where they have not built shear walls. They have new shear walls and the columns are also being jacketed to increase its capacity. New shear walls has to be erected in this manner. You see that chemicals have been used. I told you epoxy chemicals to bond the old and that is the old steel and new steel along with the concrete there. It has to be welded. It's better to be welded. New shear walls being erected and the new shear walls which have been placed, it should be placed symmetric in plan. Even though it is going to be erected in an already existing structure, it should be, the plan should be worked out such that it is placed properly, symmetric in plan, or else it becomes useless. The retrofit becomes useless again. The shear wall is going to give a better lateral load resisting capacity, increasing the ductility of the structure too. FRP is another type of repair. Now, why do we go for, when do we go for design of a repair? When there is insufficient material strength, which you get to know, compressive strength of concrete has decreased from your MDT and your condition assessment. There is a deficiency in size of the sections which is provided. Cross sections of the members, I mean to say, due to damage taken place in the structure material level because of earthquake, lack of verticality of columns, especially I just wanted to put that figure here. See, they have not maintained the centering was not placed properly. This you will see that in many structures, it's a fact. They don't maintain the plumb, I mean to say the verticality. In such cases, when the earthquake takes place, there is higher liability for damage and settlement of structure due to poor ground and soil conditions. So, another seismic retrofit, I want to put it on record. IS code for seismic retrofit is IS 15988, which is used for RC jacketing as well as of existing structures. Seismic evaluation and strengthening of existing structures is IS 15988 2013, and for RC jacketing and FRP, both are existing, which you can make use of to design. And for FRP, I'm sorry, ACI 440 has to be used because we don't have any Indian code for FRP repair. Let me tell you. So ACI 440 to be used. I don't have time to run through this, but I'll come to it later. It's basically to enhance the compressive strength of concrete. The confinement is to be increased. So here you see that another way is to provide infill walls. Okay, I would very briefly run through a case study which I have done, a global retrofit where a shear wall has been introduced in an already existing structure. This is out of Bangalore, which we have done. It's an older file because it was done earlier. You can see that a shear wall, the building didn't have a shear wall. We tried various combinations before providing it. It was a large structure of 1, 2, 3, 4. It was a 9-story structure. So we wanted to see what would be the story drifts that would take place. And eventually, not only from ETABS, we also did a finite element analysis to see which would be better. a finite element analysis to see the variation of the shear wall and if should we introduce a extra shear walls or columns. So we did see that the shear wall was a better option and feasible when compared to long term. And the another project which we worked on I worked on with Dr. Jaisima from Stedrant was that of in a building to jacket RC columns. A building which is existing in a seismic zone. These are the details. Here the column, this is the FE model of the column, which was modeled. The 3D, you would see the shear keys was modeled to find out what would be the bond stress which would develop at the RC jacket and column interface. That was the main thing which we wanted to see because the epoxy which we are trying to use was not giving us a confidence. So we wanted to see that and then apply it. So when we are going to do seismic retrofits like this, we need to do these kind of analysis to also gain a confidence interval, to also not only from that to make the structure safe. Now the next thing I would come to say about structural controls very briefly. What is structural controls? Is to bring down the displacements in a particular building subjected to earthquake. Basically they are passive, active and hybrid controls. I am going to talk about passive control here. What do you mean by passive control? It does not make use of an computer system. In an active control, it makes use of a computer system and an actuator to control all the particular components in that structural components which are used to reduce the displacement. Hybrid, it makes use of passive and active both. So passive control, I'm sorry, there has been a smudging of this figure. I'm very sorry about that. Passive control is basically seismic isolation, base isolation, energy dissipation devices, that is the dampers, and mass dampers, that is tuned mass dampers. So basically, I would like to talk about very briefly about base isolation. That is basically the superstructure, the base isolators are provided between the superstructure and the foundation. Okay. There are different type of isolators which are elastomeric bearings, lead rubber bearings, friction pendulum type. You see here, this is under a test. These are provided in the actual structures too. And this is the one which is provided. You see the size of this and base isolation. You'll see all this is all in foreign countries. Then you'll ask me now, where is it provided in India? See, you will see the base isolated. You'll see this base isolated building here, the cross section where the isolators are provided. This is a test which has been performed. Installation of the isolator. Now you'll ask me, where is this base isolator? I'll tell you, in India, this has been installed in Bhuji Hospital, earthquake resistant hospital in Gujarat province in India. Base isolation designed by structural engineers, Dunning Thornton consultants from Wellington, basically from New Zealand. They have designed it for this entire building because the Gujarat, you know, it is in an earthquake zone. The next energy dissipating devices are bracings with dampers in it. Viscous, I would like to talk about very, very briefly. These are the viscous dampers which you can install in buildings in between, diagonally between beam column joints in this way to improve the ductility of the structure. You can see the sizes. See, this is where one of the damper has been installed for one of the bridges. It's been installed. This is a test which has been performed here. And this is one of the damping device which have dampers which have been provided to rehabilitate a school in Italy. See, this gives you, see, we study all these things, but only when we put it to practice, you get the confidence. When you see that this has been applied. The next is the tuned mass dampers. The tuned mass dampers are, I'll just tell you very, very briefly, to reduce the displacement, especially the drifts in buildings, very large, tall structures. This is the one which is provided in Aspire Tower in Doha in Qatar. So in this, you would see that the comparison between the control systems itself, isolation is better, energy dissipation or mass dampers. You would see that the mass dampers are the ones which will help, which takes into account from economy and from, though they are expensive. I would not say that they are less expensive. They are expensive in an Indian scenario, but from a application and restoration point of view, when compared to the isolation and mass damper system, the dampers, especially passive dampers, viscous dampers, play a better role. Now, the whole point I would like to conclude here. I'm sorry, I've taken 5 minutes of your time. Yes, it's up. The time is up. I would like to conclude here. I would put it on record here. See, we need to make our structures into which are going to be constructed are going to be designed and which are going to be constructed to make it ductile, or already if they are designed, we have to make use of the existing measures to see to it that it caters to the strength, stability and economy point of view also, to make the structure ductile such that it does not collapse, causing fatalities. Thank you. I'm sorry I've taken 5 minutes of your time. Here to take questions.
Yeah, thank you very much, sir. I would like to thank Dr. Guruprasad for the presentation on rehabilitation and ductility requirements for the seismic resistant design.
I would like to just take 1 second. I would like to show the participants here what happens with the isolation. Okay.
Due to the time constraint, we request Dr. Guruprasad sir to, just close the session. Now, if you have any questions, you can just post it in the chat box for the any questions. I think most of the questions during his presentation time he has answered.
I will just answer.
I will answer these questions. Should beam reinforcement be induced inside column for ductility design of earthquake resistant structures? The beam reinforcement has to go into the beam column joint. How do 1 second? It should go into the beam column joint, as I told you, to provide anchorage. Okay, so that there is no opening up of the joint. What are the best construction methods to be used to construct a multi-storied building withstand earthquake against to withstand against earthquake? See, basically you have the RCC conventional construction. At present, if you take places like if it's in zone 3 up to zone 4, your ductile detailing consideration is will be able to take into consideration the stability of the building. Apart from that, if they are very important buildings, you can go for installation of bracings also into the structure and shear walls in the exteriors to restore the stability. Okay. What are the effects of torsion on beam column joint, that and there is any experimental method to find out torsional moment of beam column joint? Okay, good question. See, basically the beam column joint, if you see, is a junction where two members meet there. So the torsion, usually what happens is the torsion takes place at the zone where, at a portion little away from the joint, when the torsion takes place also, which also leads to causing the hinge formation. But if the joint itself is going to it's going to have torsion, yes, as you said, it has happened in many cases. There you have to provide, that's what is the whole point of ductile detailing. You are going to provide lateral ties inside the particular joint to take care of confinement, to avoid this to a large extent. But if the magnitude of the earthquake is so huge, it is going to cause it, then it is unfortunate. You can use steel plates. You can adopt steel plates at beam column joints to counteract this, actually, in case of RCC. How do compared, how do compared capacity with demand? See, basically, okay, how do you compare capacity with demand? See, structure has its own, capacity for resisting the earthquake. And the demand is based on what would be the magnitude of for what you are going to design for. How do you compare capacity with demand? So basically here, the capacity here is, both are interrelated, I can say that, because your demand is based on where you are going to design the structure. In fact, if it's going to be in zone 2, zone 3, zone 4, zone 2, not much of, you don't have vulnerability. But when you go from zone 3 to zone 5, your vulnerability is more towards earthquake and damage. So there your demand is more, and your capacity of your structure should cater to it. That will reflect onto your design. How do we design plastic hinges for inclined members, say in structures such as diagrids? See, diagrids, if you take, when you take diagrids, the diagrid is basically you're going to take even steel members, steel structures where you're going to use pipe sections also. So in that cases, it's the joints which you have to take into considerations. Yes, what you say, plastic hinges, if it does form there, you have to do an analysis to see to it that through a as we discussed, to see where the hinge formations take place. Based on that, you have to what you call tweak your design to look into your section considerations. Maybe you have to go for a slightly higher section. How can I compute moment curvature and theoretical relationships? Moment curvature. See, basically moment curvature, you have your bending moment which is acting. Okay, you have your moment curvature relationships comes in when you're having your bending moment acting on the particular structure. Especially you take the beam. For a beam, when you apply a particular load, you're going to develop a moment. So for that, at that particular point, if you are going to have curvature there, you take the tangent there, you're going to get a slope. Basic, I'm saying basic stuff. So from through that, you are going to, for different loading, your moment goes on varying as well as your curvature. So you plot with respect to that, you develop your moment curvature relationships. Okay, I hope I answer. How shear wall is different from lift room wall construction? Okay, very good question. Sir, actually, if you see, your lift room wall is a shear wall only. It's a reinforced concrete wall. Okay, basically, you know, when the lift core wall is provided, I do not know if any one of you are purchasing a flat, please go and check your, because you're putting your valuable money, you go and please check the structural drawings. Ask that contractor if that person is providing a reinforced concrete wall, because a reinforced concrete lift core wall is also a shear wall. Okay, it should be designed because that itself will be a central core or attraction for all the in-plane shear in that particular direction if the earthquake takes place. Actually, that's how it should be designed for. Only in cases where a structure is going to be located in a very vulnerable earthquake zone, like zone 4, zone 5, a single lift core wall will not be sufficient to resist that earthquake. And in that cases, as you saw, we provide external shear walls to take care to resist the shear due to earthquake, in-plane shear. So basically a lift room wall, a lift room reinforced concrete wall I would define is a shear wall only. It should be designed like that. It should be. Okay, it is like what you say for a disease, there is a particular disease, one particular medicine should be given for that only, but unfortunately something else is given to mask it. It's what unfortunately is happening today. So I guess I answered some of the questions. I hope I've answered all of them.
Okay, I would like to thank again Dr. Guruprasad for answering most of the questions posted by the
YouTube.
Participants. Now, on behalf of Department of Civil Engineering, Ramaiah Institute of Technology, I would like to thank again Dr. Guruprasad for the present. I mean, we have participants. We have shared the feedback link. Kindly answer for the feedback link, and we'll be meeting tomorrow at 10:45 for the day 2 presentation. Okay, the same link will be maintained for the tomorrow also. You can log in through the same link. Thank you once again, everyone.